Okay, welcome to lecture 29. We're still on unit 4, and we're solving systems of linear first order equations. And so we're just picking up where we ended up last time. We're working on homogeneous linear systems with constant coefficients. So last time we covered case 1, which was the case where we had distinct real eigenvalues to the coefficient matrix A. We also covered the first part of case 2, which is where we had a repeated eigenvalue with a full set of eigenvectors. And today we're moving on to case 2, repeated eigenvalues when we do not have a full set of eigenvectors. And then of course we'll cover case 3, which is when we have a complex set of eigenvalues. Okay, so just a quick reminder, we can write our linear system of ODEs in matrix form as x prime equals a times x, where a is this matrix of coefficients. Okay, so again we're dealing with homogeneous systems here, so there's no plus f over here at all. We're only dealing with homogeneous systems here. Okay, and recall that we can calculate the eigenvalues of matrix A by solving this determinant equation on the right hand side here. And then once we have the eigenvalues, we can calculate the associated eigenvectors, which we were calling k here. Okay, so example 2, repeated eigenvalues without a full set of eigenvectors. So let's consider the system here. So I just had to fix up the fact that the derivatives on the left here. So x prime equals some linear function of x, y, and z. So x, y, and z are the dependent variables here. We could potentially assume that t is an independent variable. So we've got a differential equation for each of these dependent variables, x, y, and z. Okay, and we can write this in matrix notation as x prime equals a times x, where a is the coefficients of these dependent variables in each of the equations. So the first row is the first equation. The last row is, of course, the last equation. The first column are the coefficients of x, so 1, 0, 0. The last column, the coefficients of z, so 1, negative 1, 2. And so we get this matrix A here. So this is a diagonal matrix, which means we can immediately, this is a upper triangular matrix, which means that we can immediately see that the eigenvalues of this matrix are going to be 1, 2, and 2. Okay, so an upper triangular matrix has the eigenvalues on the diagonal. All right, so again, from first year linear algebra. So we have an eigenvalue lambda 1 equals 1 with multiplicity 1. And then we have a repeated eigenvalue lambda 2 equals 2 with multiplicity 2. So if we focus on lambda 1 equals 1, the non-repeated eigenvalue, it's not too hard to show, and you might like to pause this video and do this as an exercise. It's not too hard to show that the eigenvector associated with the eigenvalue 1 is k1 equals 1, 0, 0. Okay. So, well, maybe you'd like to go try that now. But, okay, what we're really interested in case 2, though, is the repeated eigenvalue. So for lambda 2 equals 2, so for this eigenvalue, we're solving the system A minus lambda 2I times k2, we're trying to find k2, equals the 0 vector. So if I take my matrix A and I subtract the eigenvalue of 2, then I get, on the diagonal, then I get 1 minus 2 is minus 1, 0 and 0 on the diagonal. So I get the system here that I need to solve. Okay, well the bottom row tells me no useful information because it just says 0 equals 0. But the middle row tells me that k3 must be equal to 0, because if you read this row, it says 0 times k1 plus 0 times k2 minus 1 times k3 equals 0. So k3 must be 0. Okay, well the top row tells me, keeping in mind that k3 is 0, it tells me that negative 1 times k1 plus 1 times k2 plus, well, k3, 1 times k3, which is 0, equals 0. So I get this equation, negative k1 equals k2, or in other words, k1 equals k2. So from these equations, I can define an eigenvector k2 to be 1, 1, 0, because look, k1 has to equal k2 here. And k3, we said had to equal 0. So we found one eigenvector associated with this repeated eigenvalue. But we need a second eigenvector, right? We need 3 eigenvectors for this 3x3 system we had to start with. But at the moment, we don't know what our third eigenvector is. So we're only able to find one eigenvector associated with this repeated eigenvalue of 2. So we need to find the second eigenvector. All right, so we're trying to find, we've got k1, k2, and we're trying to find k3. So from the last class, there was a slide that we put in there that said if there is only n minus less than m, so here 1 less than 2 eigenvectors corresponding to the eigenvalue of multiplicity 2, then 2 linearly independent solutions to the system are, so this is eigenvector times e to the lambda 1, the eigenvalue times t. But really this line is what I'd like you to look at, okay? We're going to try to define an eigen or a solution to our system, a second solution to our system of this form. So an eigenvector times t times e to the lambda 1t plus the other eigenvector times e to the lambda 1t. Okay, so we're going to have a combination here. So let's take x3 in this form then. So k2 is the eigenvector we've already found, times t, e to the lambda 2t, we know what lambda 2 is, plus k3, e to the lambda 2t. So k3 is the thing we don't know here. So this is what we're going to try to find. Let's use this solution, x3, in the ODE system, okay? So we need to take the derivative of x3 and multiply x3 by a here. So if we do that, we get something like this. So this first term, these terms on this left-hand side is x3 prime. Okay, so x3 prime is going to have 3 terms because here we have a product rule. We have a t times an exponential of t. So we have a product rule here, so that accounts for the first 2 terms in brackets here, plus the k3 e to the lambda 2t term. When I differentiate that, I bring down a factor of lambda 2. So I get that here. So these 3 terms here are just the derivative of x3 with respect to t. Okay, the right-hand side is just a times x3. So in each of these 2 terms in x3, we just have an a multiplying on the left-hand side. And so remember that with matrix multiplication, the side you're multiplying on matters because a and the k's have a certain size, right? So the a's come from here and the x3 is there. Okay, so now I can rearrange this equation like so. So I can get the t times e to the lambda 2t terms all together, and I can get the e to the lambda 2t terms all together, and rearrange that so that that equals the 0 vector. Okay, if I highlight, if I look at this t e to the lambda 2t terms here, that is only 0 when t equals 0 or t equals minus infinity. This term here, e to the lambda 2t, is only 0 when t equals minus infinity. So if I want a solution for general t, so any value of t, I want this to be true for any value of t, then both of these terms in red must equal 0 exactly. And in fact, they should be the 0 vector. So I can write these equations out one by one. So k2 times lambda 2 minus a times k2 equals the 0 vector. Well, actually, this is equivalently written like so, right? A minus lambda 2I times k2 equals 0. This is already satisfied. We already satisfied this equation because lambda 2 equals 2 is an eigenvalue and k2 is an eigenvector. So this equation, or this term in red, first term in red here, is already automatically satisfied. It's already automatically equal to 0 because lambda 2 is an eigenvalue, k2 is an eigenvector associated with lambda 2. However, this second term here, we can rearrange that to a minus lambda 2I times k3 equals k2. Okay, so this gives us a way to find k3. This equation here is the equation we need to solve to find k3. Okay, so this is really similar to an eigenvalue equation, except for the right-hand side is not equal to the 0 vector. It's actually equal to the other eigenvector that we found, okay? And I guess to be specific, we couldn't use k1 here because k1 was associated with lambda 1. We have to use the other eigenvector associated with lambda 2. So lambda 2 here is 2. The eigenvector we found was k2. Okay, so let's write that out. A minus lambda 2I is this matrix here. K1, K3 is this matrix here with K1, K2, and K3. So we're trying to find these unknowns here. And the right-hand side now, instead of 0, 0, 0, this is equal to K2, which we showed was 1, 1, 0. Okay. So let's solve these equations now. Let's read off what the solution is. So the bottom line tells us no useful information because it just tells us that 0 is equal to 0. The middle line says 0 times k1 plus 0 times k2 minus 1 times k3 minus 1 times k3 equals 1. Or in other words, k3 equals minus 1. The top line tells us that minus 1 times k1 plus 1 times k2 plus 1 times k3 equals 1. Okay, but k3 was equal to negative 1, so we end up with negative k1 plus k2 equals 2. Or I could rearrange that for k1 to say k1 is equal to k2 minus 2. So let's just choose k2 equals 2 for now, which means that k1 would be 2 minus 2 or 0. So our third eigenvector to the system is going to be 0, so that was k1, 2 for k2, and k3 we said had to be equal to negative 1. So now we have three eigenvalues, lambda 1 equals 1, lambda 2 equals 2, repeated, okay? And now we have three eigenvectors, okay, k1, k2, and k3. So we can write down the general solution to this ODE system then. Okay, and that is simply x is equal to some constant c1 times e to the t 1, 0, 0. So this first term here is the solution associated with the non-repeated eigenvalue, lambda 1 equals 1. And then we start to get the solutions associated with the repeated eigenvalues. So plus c2 e to the 2t 1, 1, 0. So this second term here, this is the term associated with the lambda 2 equals 2. So that's how we e to the 2t, that's our lambda 2 is the 2. And the second eigenvector k2, which is 1, 1, 0. Okay, and then the third solution here in brackets c3. So we have t e to the 2t times k2, 1, 1, 0, plus e to the 2t times k3, 0 to negative 1. And of course, we can pull out the common factor of e to the 2t there if we so choose. And we have an extra equals here. I don't know why. It's obviously just a small mistake there. Okay. So let's just summarize what we've done for case 2. So case 2, find the eigenvalues of the matrix A, solving this determinant equation, just like in first year linear algebra. If lambda 1 equals A, multiplicity equals 2. So if we have a repeated eigenvalue, in other words, we need to calculate the eigenvectors by solving this equation here, A minus lambda I times K equals 0. If it so happens that we find two linearly dependent eigenvectors, K1 and K2, then we have a full set of eigenvectors. So two linearly dependent solutions to the system of ODEs is x1 equals the first eigenvector e to the lambda 1t, x2 equals the second eigenvector e to the lambda 1t. So if I have a full set of eigenvectors, it's fairly easy. However, if we only have one eigenvector, so let's say we can only find k1, then we have to solve an extra equation. So we have to additionally solve this a minus lambda 1I times k2 equals k1. So remember, we know what k1 is equal to, we're trying to find k2. And if that's the case, then our two linearly independent solutions to the system of ODEs, x1 equals k1, the first eigenvector that we could find, e to the lambda 1t. So that's the same as in 3a. So these x1s are the same in 3a and 3b. But in the case where we couldn't find the linearly independent solution, then we have a solution in this form. E to the lambda 1t, again, we know the eigenvalue lambda 1, times t times k1. So k1 is that first eigenvector that we could find from solving this a minus lambda I times k equals 0 equation, plus k2, where k2 is the eigenvector that we had to find from solving a minus lambda 1I times k2 equals k1. And so then the general solution to the system of ODEs, linear homogeneous ODEs, is just the linear combination of x1 and x2. So let's do one more example of this case. Well, maybe I'll just go back a slide and say, this is a very important slide for case 2, and it's probably the hardest case, is 3b. So maybe you might like to add this slide to your favorites or something and have it as a reference slide. Let's look through an extra example here. So we're going to just look through a 2x2 system here. So x and y are the dependent variables here. And I can write this in matrix form as x prime equals a times x, where a is 2, 2, 0, 1. So the 2 on the diagonal here and 0, 1 here. Again, this is an upper triangular matrix, so I can see that my eigenvalues are going to be 2, multiplicity 2. If I calculate this a minus lambda 1I, I remove 2 on the diagonal, so I end up with this system here. Okay, and so the eigenvector associated with this eigenvalue is, you can pretty easily show, is going to be 1, 0. Okay, so we only have one eigenvector for this 2x2 system, so we must find a second solution. Okay, but remember what we said is that now we must solve a minus lambda 1I times k2 equals not 0 vector, but k1. Okay, and we're solving for k2. So k1 is the first eigenvector that we were able to find. So again, 0, we have a minus lambda 1, a is 0, 0, 0, 1 times k2. So this is this unknown that we're trying to find here, equals k1. So now k1 equals 1, 0. Okay, and if we read off what this is telling us, we have 0 times k2 times plus 1 times k2, 0 times k1 plus 1 times k2 equals 1. Okay, so therefore k2 has got to be equal to 1, and k1 can be anything, so let's just choose k2 equals 0, 1. And so therefore the second linearly independent solution is e to the 2t times t times k1 plus k2. Okay, so we have now we have two linearly independent solutions, x1 over here and x2 over here, and so the general solution to this system of linear homogeneous first order ODEs is the linear combination of x1 and x2. Okay, so let's move on to case 3, complex eigenvalues. So let's let lambda 1 equals alpha plus I times beta, where alpha is the real part of the eigenvalue and beta is the imaginary part. So let it be a complex eigenvalue of the coefficient matrix A. And so we're going to let K1 be the eigenvector associated with lambda 1. Okay, and therefore the solution to our two solutions to this system are going to be x1 equals b1 times cosine of beta t minus b2 times sine of beta t times e to the alpha t. So remember that alpha is the real part of the eigenvalue here. Beta is the imaginary part. And I haven't told you what b1 and b2 are yet. But these two solutions are linearly independent solutions on the whole real line. B1 is going to be the real part of the eigenvector. B2 is going to be the imaginary part of the eigenvector. And then, of course, the general solution is just going to be the linear combination of x1 and x2. Okay, so in this case, as long as if we find a complex eigenvalue, then we should be able to find an eigenvector, associated eigenvector. We can look at the real and imaginary parts of each, real and the imaginary parts of each, and then we just have to basically substitute those into this solution, these solutions x1 and x2. Okay, let's look at an example then. Okay, so we have this 2 by 2 system here, and we can write this as in matrix form, of course. So x prime equals a times x. A is going to be the coefficients in front of the x and y, so 1, -1, 5, -3. Okay, and we're going to want to find the eigenvalues of this matrix. And so just as a side note, the eigenvalues of a 2 by 2 matrix are often found more easily using the following facts. So of course we can always solve this determinant equation to find the eigenvalues, but we also know that in any matrix, the sum of the eigenvalues is equal to the trace of the matrix. And we also know that the product of the eigenvalues is equal to the determinant of the matrix. So for a 2 by 2 system, this often simplifies things quite a lot. So let's just check out, what is the trace of this matrix? Okay, so 1 plus -3 is -2. What is the determinant of this matrix? 1 times -3 is -3, minus 5 times -1, so we're going to add 5, so that's equal to 2. So the trace of A is equal to 2. The determinant of A is equal to 2 as well. The trace of A is equal to -2. The determinant of A is equal to 2, so the sum of the eigenvalues of this matrix are equal to -2, and the product is equal to 2. And of course we have 2 eigenvalues because we have a 2 by 2 system. So this first equation here, I can rearrange this for lambda 1. So lambda 1 equals -2 minus lambda 2. And then I can use that in the second equation here, which we got from the determinant of A. So instead of lambda 1 times lambda 2 equals 2, I can write lambda 1 as -2 minus lambda 2, all multiplied by lambda 2 equals 2. That is just a quadratic equation, right, when I expand the brackets here. So I can solve that quadratic equation. So lambda 2 is going to be -1 plus or minus I, and lambda 1 is going to be the complex conjugate of lambda 2. So therefore my 2 eigenvalues for this system here are -1 minus I and -1 plus I. Okay, so let's just identify the real and imaginary parts here. So my real part is going to be -1, and my imaginary part is going to be, well, 1. I can choose that to be 1 here because we're multiplying this one here by 1, this imaginary number by 1. And then I need to find the eigenvectors associated with these eigenvalues, right? So I'm solving this equation, A minus lambda I times K equals the 0 vector. So on the diagonal, I'm going to subtract lambda 2. So 1 minus -1 plus I, -3 minus -1 plus I. And if I solve this system, Or if I write out the equations, then I get 1 minus 1, 1 minus minus 1, which is 2, take away I. So I get 2 minus I times K1, minus 1 times K2 equals 0. And then in the second equation, I get 5 times K1, minus 3 minus minus 1, so minus 2, take away I, times K2 equals 0. So I get these two linear equations that I have to solve here. Okay, looking at this first equation, I can therefore write K2 is equal to 2 minus I times K1. Okay, and well, I can write K1 equals S. So if I let K1 equals some value S, then K2 is equal to 2 minus I times S. And so therefore my eigenvector K1, well, let's just let K1 equal, let's let S equal 1. So 1 equal, K1 equals 1, 2 minus I. Okay, so now I have my real and my imaginary parts of my eigenvalues, my eigenvector. Well, I need to look at the real and the imaginary parts of my eigenvector. So the real part of K1 is 1, 2. The imaginary part is 0. There's no imaginary part in this first entry, 0 minus 1. So I can write my B1 and my B2 as the real part of K1, 1, 2, and B2 is the imaginary part of K1, which is 0, negative 1. Okay, remembering that now that I have alpha and beta and B1 and B2, I can just simply substitute these values into these two equations here. So, so I have the general solution to this system is C1 times e to the negative t. So the negative 1t here comes from alpha multiplied by the real part, or B1, the real part of K1. So B1 is 1, 2 cosine of t. So the 1 times t here comes from the beta equals 1 minus B2, so 0, negative 1 times sine of t. So this is x1 here, plus some constant c2 times e to the alpha t, so negative 1 times t, times B2, 0, negative 1, cosine t plus B1 sine of t. Okay, so I guess the key message here is that case 1 and case 3 are relatively straightforward as long as you can find eigenvalues and eigenvectors. Case 2 is much more challenging if you cannot find a full set of eigenvalues, but there's basically just an extra step in that case 2b. But really the key message is that if we have a linear system of equations, a homogeneous linear system of ODEs, then we can find the solution by calculating the eigenvalues and the eigenvectors of the coefficient matrix. As long as if we know how to calculate eigenvalues and eigenvectors, then well, we should be able to find the solution to these systems. Okay, great. I'll see you in the next class.